Welcome, everyone. I'm really very happy today to welcome one of my MIT colleagues, Kerry Emanuel, who is a professor of atmospheric science at MIT. Kerry is in the what is called the Earth, Atmospheric and Planetary Sciences Department. Those of you who've been on the MIT campus recently or in the last several decades, I guess I'd say, will recognize the building in which that department is housed, which is called the Green Building. It has, it's vertical. I think it is, Kerry, the tallest building on the MIT campus. And it has on its top a radome, which is used in, as I understand it, used in radar weather forecasting, weather tracking.
It was.
So, yeah, good. So you may be interested in knowing why it's called the Green Building, folks on the line. It's named after Cecil Green, who was, among other things, a philanthropist of great distinction, but also one of the founders of Texas Instruments. And he was also a geophysicist. So, you know, in lots of ways, it makes perfect sense that the building which houses the Earth, Atmospheric and Planetary Sciences Building should be named after Cecil Green. So I'm happy about that, and I'm delighted to introduce one of the world's experts on atmospheric and climate matters, Kerry Emanuel, to join us today. He's been described as a climate scientist for nuclear energy. And I think that's actually quite an important distinction, and you're going to understand why that distinction applies when you hear Kerry's talk today. Some of you will know that Kerry prepared an essay for the 50th anniversary issue of The Bridge, and that essay is on nuclear salvation, which is the title of the presentation today. So, Kerry, welcome to the Wilson Forum. It's good to see you again, and the floor is yours, sir.
Well, thank you, Ron. It's a great pleasure to be with you. I wish you could be with you personally, but maybe that day will arrive.
Let's hope so.
Let's hope so. And thank you so much for inviting me to talk about that. As Ron indicated, I'm a climate scientist. I'm not a nuclear engineer, but when you get really into climate risks, which I'll talk about today, it's natural to start to ask the question, you know, what can we do about it? And when I talk, I do a lot of public outreach. When I talk to the public, it's the first question they ask, which I think is natural. So I've tried to teach myself how to answer it over the last 15 or 20 years. And I know some of you know an awful lot more about nuclear power than I do. So please don't hesitate to correct me if I go astray. So I'm going to try to share the screen here, if I can figure out how to do it. There we are. Can you all see that? Okay.
Yes. There you go. Yep.
Okay. Yeah, there's a bit of a lag, but there it is. And okay, so I'm coming at this from the point of view of climate risk, and I want to make the argument that nuclear power is going to have to, unless there's some miracle somewhere else in the technological front, have to play an important role in this. So what I'm going to do is just give you a very, very light talk about climate, just a few slides. You know, I could spend the whole talk easily on that, and you have my primer. But really get very quickly into the subject of what really are the risks, because 3 degrees of warming by itself is not a risk, that, at least not for most people. That isn't the problem. The problem is the things that go along with that, and why I would argue we need nuclear power. Not just nuclear power, but certainly some nuclear power. So it boils down to this chart in some ways. This is just a pie chart showing the composition of the atmosphere, with the provision that some things like water, well, really only water vapor on this diagram, is highly variable in space and time. The others are pretty well mixed until you get up into the mesosphere. So as everyone is aware, it's mostly nitrogen and oxygen. Argon is about 0.9%. And then, of course, there are a lot of things that aren't on here that are really in trace amounts, but water vapor, which is a very important greenhouse gas, on average is 0.25% by mass, and carbon dioxide on average about 0.04%. So that carbon dioxide and water, the two most important greenhouse gases, are in that little orange slice, which if you have a hard time seeing, well, that's intentional. It's just the math. It's tiny, right? But that orange slice makes the difference between the habitable Earth with an average surface temperature of 60 degrees Fahrenheit and an uninhabitable one with temperatures well below freezing. This basic fact, and I could spend a long time talking about the physics behind it, has been known pretty well since the end of the 19th century. This is nothing new about it. There's nothing radical. There's nothing controversial about this in science. But one thing you want to understand is that in contrast to carbon dioxide, whose average turnover time is got 2 time scales, hundreds and thousands of years, water vapor has a residence time in the atmosphere of 2 weeks. It's very fast. And its content is controlled by atmospheric dynamics and temperature. That is, it's not, you can't consider it an external forcing of the system because it reacts very, very quickly to what else is going on. So water vapor is a feedback, universally thought to be a positive feedback simply because of Clausius-Clapeyron. When you raise the temperature, you get more water vapor at saturation anyway. So this leaves carbon dioxide as the main control of climate, which is remarkable, 0.04%. I always sort of think of the bead of mercury in a thermostat that controls the temperature in a very large auditorium. Yes, the world is full of big volumes being controlled by small effects. And on geological timescales, that is our thermostat. Carbon dioxide reacts in a way as to be a negative break on temperature change, but on quite long timescales, unfortunately much longer than the current human forcing of carbon dioxide. So I want to go back in history a little bit to Svante Arrhenius, Swedish chemist, Nobel Prize winner, lived at the end of the 19th and early 20th centuries. And like a lot of 19th century scientists, they dabbled in many things outside their particular field. And he wrote in 1906, based upon basically back of the envelope calculations, but using real measurements. A fascinating story, by the way, that if you were to double the CO2 content of the air, you'd raise the Earth's surface temperature by about 4 degrees, which is a remarkable number, given that it's pretty much in line with modern estimates. So a little bit on the high side, but definitely within the error bars. And he did that because he was the first to speculate that fossil fuel combustion, which while he was alive was a pretty tiny fraction of what we're doing today, would in fact at some point measurably raise the carbon dioxide content of the atmosphere. So he kind of made a prediction. And I'll leave it to you to decide whether he was right. So this is a graph going from 1880 to more or less the present, showing in blue Arrhenius' prediction of temperature, which is proportional to the radiative forcing of carbon dioxide, which in turn is proportional to its logarithm. That's the blue line. And the red is the actual temperature. Now, of course, there's a lot of things going on with global temperature. There are a lot of fluctuations that are just random. There's responses to volcanic forcing, human aerosol forcing, which is not on here, that had a big effect in the 60s and 70s and maybe 80s. But, you know, that's not a bad prediction, I would say. And it's based on solid physics. It's not just somebody's guess. There is zero doubt, among the few things we're really certain about, is that the big increase in CO2 we've seen, and I'm now showing you a chart partially based on proxy information going back 1,000 years, proxies being bubbles of gas trapped in ice cores. The CO2 really started to ramp up in the Industrial Revolution and is today actually off of this chart. I have to update this chart very often. It's way, way up here. We're changing the concentration of the most important long-lived greenhouse gas in the atmosphere by order 1. Now, one of the reasons, besides just this time series, we know it's human is because of the particular isotopic composition of the carbon dioxide in the modern era. It's another story. Now, if you look at the air temperature, which is in this case relying on proxies going back 2,000 years relative to what it was 2,000 years ago, The pink at the very right-hand side is the modern instrumental record. The blue is from multiple proxies in the Arctic, actually, and the gray is a measure of the uncertainty of those proxies. We see a long, slow decline, which turns out to be a natural response to perfectly periodic orbital variations, and which unimpeded would lead us in another 10,000 years or so into the next ice age. But that decline was reversed around 1800 or so, and it's been followed by a steep rise. Well, it's easy to talk about the past. The future is difficult to predict, excuse me, naturally. And what you see on the left are not predictions of temperature, but predictions of atmospheric CO2 emissions, including some baselines that were used in calculations done to support the most recent IPCC report, which was just released. And so the spread, this is going forward to the end of this century, the big spread there is nothing more in this case than the spread of assumptions about what we're going to do. Are we going to try to reduce emissions? Or are we not going to do anything at all? That kind of thing. So this, and then there, of course, at the end of the century, you actually start running out of fossil fuels. So that has to be taken into account in these high emission scenarios. And then on the right is the corresponding estimates based upon fairly sophisticated models, in this case, of the global mean temperature going out to the end of the century. And there's a very large spread. There always has been a lot of uncertainty going back to the National Academy report by Jewel Charney and colleagues in 1979. And unfortunately, my profession has not been very successful at beating down this uncertainty. So there is no question and there's no debate in science, in climate science, that projections of future climate are highly uncertain. And I'll come back to that point. This is just kind of an aside because I really didn't want to talk so much about the climate science today, but obviously happy to answer questions. The most important source of uncertainty are clouds. Clouds are bright in the visible, they reflect sunlight, and they're responsible for the bulk of the Earth's albedo, which is roughly 30%. But clouds also absorb and re-emit infrared radiation, and so they act as greenhouse agents. So they work both sides of the radiative street, and some of them are very thin, but extensive horizontally. They're really, really hard to model, and so it keeps us awake at night, these cloud feedbacks. So the water vapor feedback, while it's generally positive, if you want to be a little bit more precise about that, it does depend upon other things, atmospheric dynamics, so we have to work on that. Response of the ocean is still not really nailed down. And then we have another problem with both natural and anthropogenic aerosols, such as sulfate aerosols that result from fossil fuel combustion. There are a lot of sources of uncertainty in that. And the result is that if you look at projections even for something as sort of simple in concept as the global mean temperature, there's a wide spread. So what you see here is the result of running models thousands and thousands of times with slightly different parameters, with different estimates of emissions. And this is something called the equilibrium climate sensitivity. It's what happens if you double CO2 and wait for the system to actually come into a new equilibrium, which is not the same thing as the transient sensitivity we'd be worried about in projections, say, at the end of the century. But what you see is a peak in the, this is just a probability distribution. The peak is between 2 and 3 degrees, but it's a broad peak with a tail going out into positive numbers. And so the way I would characterize this, once we start to understand the risks associated with this, which I haven't talked about yet, is if we are so lucky as to wind up in the 5% lowest part of the tail, there's not much risk there. There's substantial, but perhaps manageable risks in the middle of the distribution, and there's catastrophic, some would even claim existential risk in the 5% tail. And this is unfortunately the situation we have to deal with. And this is by way of turning the page to risk. I want to emphasize this is for equilibrium climate sensitivity to a doubling of CO2, but if we don't do anything, This is a projection, again, of CO2 concentration rather than emissions. Going out to the end of the century, if this dashed line represents twice the pre-industrial concentration, we don't do anything, we're going to triple it by the end of the century. So doubling is a bit conservative, unless you're hopeful that we're going to take a lot of action to stop things. And this is just a projection based upon carbon cycle modeling of the CO2 concentration going forward, assuming that you just turn off the valve suddenly at some concentration, 450 ppm, 550 all the way up to 1200. I just want you to look at the decay rates. There's an initial quote unquote rapid decay with about a couple of 100-year time scale, and then a much slower decay going up thousands and thousands of years. So the point is, unless we can figure out how to suck carbon dioxide out of the atmosphere somehow economically, whatever level of CO2 we have when we stop, we're going to be stuck with a large amount for a very long time. And this is projections of global surface temperature that go along with that. And because of heat storage in the deep ocean, there's a compensation. The heat is still basically coming out of the system for a long time after there's a big lag between equilibrium temperature and equilibrium CO2. And so basically the first order, whatever temperature you have when you shut off the spigot, is what you're going to have for a very long time. Now I want to just turn to a little bit more in depth to the concept of risk. There's a very large literature on this, most of which was done long before climate change, but there's some very interesting aspects of it. If you take one of the more favored formal definitions of risk, it's minus the integral over all the intensity. Let's just talk about a particular hazard. It could be an earthquake, a hurricane, if you like. We have to actually sum over, in the end, sum over all those hazards. Let's just think about one hazard. So it's the integral of the cost of that hazard over changes in the cumulative probability of that hazard as a function of the intensity of the hazard. And I now assume that the cumulative probability is accumulated from right to left, which is why this negative sign is here, because the cumulative probability is decreasing as you go out. Okay, that's just a formal definition of risk. And if you sort of think about it in graphical forms, here's the probability density, that's the dP, if you will. And then this is the cost, both as a function of the intensity or magnitude of the risk. Typically, for most risks that we're familiar with, the cost goes up somewhat non-linearly with the magnitude. Okay, I'm going to come back to this point about why that's so. It, in some calculations, rises so steeply for climate risks that the integral formally doesn't converge. That is, this red curve goes to infinity before that probability curve goes to zero. You're in trouble. So, but the main point I want to make is that if you just leave the median of this probability distribution alone and fatten the distribution, that is, increase the uncertainty, obviously, if you do this integral, you're going to be increasing the product because of the fact that most of the risk is coming from this tail. Uncertainty increases risk. There are people like Steve Koonin, who I just debated a few days ago here at MIT, who argues in a book that because it's uncertainty, we shouldn't do anything about that. I don't regard that as a rational argument about any kind of risk. But the other point that's somewhat obvious is risk is strongly weighted toward the high intensity tail. And one of the problems for that, and it comes up in Steve Koonin again, if for example, most of the damage done by hurricanes is done by events whose probability is once in 100 years, or frequency. But we don't have hundreds and hundreds of years of observational records of hurricanes. So we can't formally detect trends, if we just want to look at historical data, in the things that matter for calculating risk. And this is a big problem, particularly persuading anybody to do anything who's not familiar with climate science and the Bayesian priors that we have because of the science itself. So why is climate risk dominated by extreme events? And this is an anthropological point more than anything else. It wouldn't surprise you, it's very intuitive. Societies are all around the world, different societies, different cultures, are usually pretty well adapted locally to events that are frequent. say, occur more frequently than once in a few human generations, say 100 years. That 100 years is a number that's very frequently used by the insurance industry, by the way. And conversely, they're poorly adapted to rare events. This is not irrational. You wouldn't, if you were building yourself a house, you wouldn't want it to be blown down by a 30-mile-per-hour wind if it's somewhere near Boston, would you? Because it would blow down very soon. But if you wouldn't want to spend the money to make it withstand a once in a 1,000-year windstorm. It would be very expensive to do that. So there's a sort of happy middle ground. So the one thing that follows from this is you get large increases of cost if the climate changes or something changes to make infrequent events become somewhat more frequent. Let's think about that in terms of a curve like this. This is an almost universal curve. It can be applied to any hazard, earthquakes, volcanoes. And on this axis is the percent of property destroyed by the phenomenon, and this is not the intensity of the phenomenon, but the return period associated with that intensity. And what we see over and over again, almost independent of culture, almost independent of what kind of hazard it is that the steepest part of this curve is around 100 years, and that's an anthropological point. So if something that was a once in 150-year event becomes a once in 50-year event, that's where you get the biggest increases in damage. And that happens because the human adaptability timescale is unfortunately longer than the current climate change timescale. If the same climate change occurred over 10,000 years, we would have no problem adjusting to it. Let me give you a concrete example from my own work. What we have done in trying to quantify climate risks of hurricanes is to basically develop a technique that allows us to generate tens of thousands of synthetic hurricanes in a given climate, whether it's specified from observations of the current climate or models of the future climate. It's a very interesting technique. I could spend a long time going into it. But I just want to use this not because the numbers themselves are important, but to illustrate the point. So what I've done is to, and this is for somebody who wanted to know, is I took a client's portfolio of insured property broadly distributed over the whole eastern U.S. in hurricane-prone areas. And for that portfolio, ran these synthetic hurricanes through the, 6,200 of them for each climate scenario, calculated the damage, and this is just showing the probability density that results from that calculation in the current climate, or I should say the climate of the recent past. And this is on a log scale, so the probability densities in terms of equal increments of log of damage in this case. And you notice the peak of the probability distribution is about $1 million to this portfolio. Okay, it's not the whole country, it's just one little portfolio. And then the dashed line is done the same way, but using hurricanes downscaled from the climate of the future, the end of the century, under a fairly generous emissions scenario. And there's as you would expect, maybe a rightward shift, not a really big one, but a rightward shift in the probability distribution. Okay, so that's probability. And if you were going to bet on how much of the portfolio you'd lose, you'd maybe choose the peak of the probability distribution. In an average year, you're going to lose $1 million in the old climate and a few $1 million in the new climate. But risk is the integral of cost over probability, and let's do that. So we can express that a little bit differently just by integrating by parts of the expression I showed you before, and we can express it as the product of the cumulative probability and the cost integrated over the change in the log of the cost. And that's what I plotted in red here. The blue curves are the same as before. And the scale is very different. It's over on this red side, okay? So here's the climate of the recent past, here's the climate of the future, and that's a 3.5. I should say the whole damage is just proportional to the area under these red curves. That's what this expression is telling you. So I'm taking the cumulative probability, multiplying by the cost, integrating over the log of the cost. And well, I'm not doing the integral. You're doing the integral by I. This is just the integrand. So you got a huge increase in costs because of the fact that you're in tail. Notice that this big increase is coming, centered around almost 10 to the 8th dollars. It's coming from the improbable events. I haven't shown you the actual probability, but these are in the current climate would be, among the most expensive events that you have. It's their increase that matters. And it's very hard to detect that in historical data. Now, I'm going to cut to the chase here. I worked partially with some economists at Stanford, Solomon Siang and his team years ago, to produce this chart, which is which takes into account lots of different extremes of lots of different things. Storms, heat mortality is a big one. Agricultural losses, murder rates, which are a function of temperature, anything you can think of. And looked at this as a function of the level of projection of increase in temperature and so forth. And this is the cost to the GDP per year at the end of the century, 2080 to 2099, as a function of how much the global mean temperature has changed by that point. So there's an awful lot going into it. You can see there's a big spread in these numbers. But if it's 3 degrees, we're talking about order 2% GDP. Okay. So Steve Koonin and others say, 2% of GDP, it's only a few years worth of growth. Why worry about it? We should just adapt to it. That's not a quantitatively correct interpretation of 2% from a risk perspective. And let me try to show you why that's true in a simple way. This is just a chart showing the real U.S. GDP from 1900 to 2017. It's the yellow curve. That's all it is. On average, it's going up a linear slope, which is sort of gratifying. But here is the Great Depression. Okay, I'm wondering if I could ask everyone to mute, because I don't think it's nice to hear dogs barking. So if you don't mind muting your mic, that would be great. I guess the person with the dog is not being able to hear this. Anyway, the Great Depression was associated with a peak drop of 3.3%. And it may be an average drop over 10 years of 2%. It's a huge thing. It's a big deal. That was a terrible time, the Depression. And the problem with 2% is not just the number. How long is it likely to be sustained? And I actually called up the co-author of the paper, and the co-author wrote this back to me. Many people don't appreciate that it's a few percent per year, every year for a long time. That really is borderline catastrophic change. And so when you hear say, it's only 2%, no, that's an incorrect interpretation. To say that that's immaterial or inconsequential is just plain mathematically wrong. Now, I want to make another point on this graph. You see that bulge up? That's World War II. Okay, a lot of people say Roosevelt sort of ended the Depression partially by getting involved in the war, but forget about whether that's true or not. At the peak of the war effort, we were spending 40% of our GDP on the war effort. 40%. Okay, and it didn't seem to hurt the economy. I'm sure it would have if it had been sustained for a long time. And it's just, to me, discouraging that we have people like Koonin going around saying, 2%, if we spend 2% of our GDP to mitigate this effort, it's economic Armageddon. Come on. The greatest generation spent 40%, but our somewhat more cowardly generation shrinks from 2%. I don't get it. Here's another thing that's more relevant, perhaps, to current times. This is the GDP percent change from the preceding quarter that over the last 3 years that shows the big effect of COVID. We had a huge downturn and then a recovery. Okay, so that by the time the whole thing was over, it really didn't affect where we were at, but we lost globally about 5 million people so far, more than World War II. So this is just to illustrate the GDP doesn't tell us everything. All right, it's not a universal metric of human suffering, and we have to take that into account too. This is from Solomon's paper too. I'm not going to spend the time to go over this a lot, but this is just the just showing the various different kinds of risks. Blue is actually mortality, and that's dominated by heat. And then yellow is energy. This is because fossil fuel combustion produces particulates, which cause premature death. And you can see that the economists have had to go into a lot of different things that make up the total percentage of GDP. And if you just take some of these estimates, central estimates, and you break them down by county, U.S. county, and this shows how they're distributed. So this is damage relative to county income from the poorest counties to the richest, and you can see that there's a huge spread there. That is, the poor counties are disproportionately suffering from the effects of climate change. So there's also the sort of societal concerns about how climate damages are distributed across the society. And none of this analysis accounts for what climate scientists regard as very low probability, but not zero probability catastrophic events. Rapid acceleration of ice loss from Greenland and West Antarctica are sort of on the top of the list, and that's because we know that we don't understand how massive sheets of ice move across bedrock. There are big accelerations of this movement in certain parts of Greenland and West Antarctica today. We don't know enough to really understand why that's happening. We're beginning to, but not nearly to the point where we're willing to predict it. But it's happened in the geological past as a response to natural climate change. So one has to worry about that. We know from models that even if you don't change the forcing, climate seems to have multiple stable equilibrium states. It's intransitive mathematically. And if you push it hard enough, you might snap it into a different equilibrium state. And we know that happens in models. We see evidence that that happened in the geological past, but we don't know enough to predict it. So none of the IPCC reports or anything like that take into account stuff like this. This is what keeps me awake at night, and it keeps the DoD awake at night. They're just about to release a report, just on the cusp of releasing a new report about this, is that we know that when you have food and water shortages, which are a big problem, consequence of climate change, that it's a big instigator of armed conflict. And you have that going on in a nuclear armed world. This is a problem, and it's right up there near the top of the list of national security threats, not according to people like me, obviously, but according to people who work in the DoD. And you will see that make big headlines over the next few weeks as these reports come out. We're also dangerously changing the oceans. The temperature is one thing, but the big problem is that we're dissolving a lot of CO2 in the ocean. About half of what we put in the atmosphere winds up in the ocean. It's lowering the pH of seawater measurably, and it's causing or threatening to collapse certain parts of the marine biosphere, and we don't know how to predict that either. So we have to worry about these things, even though we're not yet to the point of really being able to quantify those. Well, again, this is 10 years old, but the DoD was already worried about climate change back then. You can read that. Climate change contributes to food and water scarcity, which increases the spread of disease and may spur or exacerbate mass migration. A lot of social scientists say this is already happening in places like the Middle East and North Africa. That's the map showing the change in pH of ocean water over 30 years. It's where you see red, it's going down. All right, now let me just try to turn now to the last topic, which is what are we going to do about this? But before we get into that a lot, we tend to focus, and the media focuses, I would say, exclusively on risk, or catastrophic outcomes, whatever. But there's also the flip side of risk, which is opportunity. And whenever you have a change in the system, for some people or some countries, there's an opportunity associated with that. And I'm not trying to be Machiavellian here. I think this is real. Where there is risk, there's opportunity. And what is the opportunity? Well, if we're talking about transforming energy, the current global energy market, actually this is a little old, it's closer to $8 trillion today, about a third of US GDP. It's a big market. And there is demonstrably an increasing trend toward decarbonization globally. You can argue about whether you like that or don't like it and whether you think it should be happening or not, but it is happening as a matter of fact. And it's this low carbon energy market is demonstrably being captured by China. That's just the reality. But I would argue that the US still may have an edge in technical innovation. And in terms of transforming the global energy system, there are, of course, global net transition costs, but nations that lead in low carbon energy technology and can export it may very well come out ahead. So I like to tell people in the United States who are really worried about the economy that it's not entirely about the risk to the economy, it's also about the opportunity to the economy. And the nations that develop some feasible kind of low carbon energy will clearly have an edge here. All right, with that said, what are the sources of greenhouse gases? What is it that we have to decarbonize? And so the pie chart on the left basically shows sources of global sources of greenhouse gas emissions. And most of it, 72% of it's energy. But there are a non-trivial amount is from directly from industrial processes that don't involve combustion. Agriculture is actually a big piece of the pie. Waste, methane released from waste principally, changes in the biosphere brought about by land use changes. I don't know what this bunker fuels is, frankly. Now, if we take just the energy part of this, 72%, and break it down, electricity and heat are 31%, transportation 15%. It's interesting that we talk about almost exclusively about electricity, which is not even all of this orange sector. It's about 25% at most of the global carbon emissions are from the generation of electricity. Transportation, manufacturing, high temperature heat from fossil fuels mostly, other combustion, and so forth. So it's a big task, and it's not just about electricity. Again, taking this 31%, 72% comes out to about 25% of the problem. Now, of course, you can electrify some of these things that aren't electric. Transportation, we're talking about going to electric vehicles, for example, and some piece of this chunk manufacturing, but it's not that simple. Some of the industrial processes, things like the manufacture of steel, require very high temperature heat. You can do it electrically, but it's not clear today that you can do it economically electrically, and it's mostly not being done that way. Okay, and so we have this projected growth out in the future of greenhouse gas emissions, assuming we don't do much about it. It continues at roughly the current rate. So what is it we have to do? We have to, if we're going to mitigate this, we have to decarbonize the global economy. And this could be, if we knew how to do it, not actually decarbonizing anything at all, but taking carbon out of the atmosphere directly, if we figure out. This is a really important point that does not get made nearly enough. And it's not just about decarbonizing what we've got. Economic development of currently poor nations depends crucially on greatly increasing per capita energy consumption. And this is a really fascinating, I can't remember if I put it there, problem, because this is also a key to reducing population growth in those countries. And population growth is one of the main drivers of the increase in CO2 emissions. So you come full circle. If you curtail economic growth, not only do you not attack the poverty problem, but you may actually end up in the long run increasing greenhouse gases because of much larger growth in population. So we have to I'm a strong proponent of encouraging economic development in poor countries. The whole world problem doesn't boil down to climate. There are all these other problems, but they play into each other. We have to take that into account. And so we have to account for rapid growth in energy. And we would require rapid growth in electricity production if we want to decarbonize transportation. But that doesn't have to take the form of batteries, it can be synthetic fuels, and hydrogen, and so forth. There's still a non-electrical energy demand for high-temperature industrial applications. There's people talk about conservation will help, but it just won't put much of a dent in any of this stuff. So what does it take to decarbonize? Well, the people who study this professionally say if we allow for hope for and expected growth in countries like India, by 2040 we're going to need twice as much electricity as we're consuming today. So 5 trillion watts in round numbers. That includes the idea that we will electrify most of the vehicle emissions. So, and then that's just electricity. Total projected global energy consumption is 25 trillion watts. All right. This is what we're up against. It's not just decarbonizing electricity, and it's not just decarbonizing what we've got. I don't know why this doesn't get talked about, but the numbers are really staggering that we have to deal with here. And so how are we going to do that? And what's on the table now is a lot of enthusiasm for renewables, which in practice means solar and wind. It should mean hydro too, but hydro is pretty well built out around the world. There's not much opportunity for expansion. We have rapidly falling prices of solar PV and wind turbines, which is very encouraging. And at low market penetration, say less than 30%, we can deal with the intermittency of these sources mostly through base load, which in practice means around the world mostly coal and natural gas. But one important thing you have to do is to understand that to do this, you have to maintain full capacity. You don't have to be generating at full capacity, but you have to have the means of generation, because there are going to be times and places where you're not generating any electricity from renewables, weather situations, and so forth. So you have this big overhead capital costs. So at high market penetration, if you're going to use the renewables at high market penetration, you're going to have storage, because you're not going to have, by definition, enough backup to do it. And the best current and near-term projected storage methods at scale are lithium-ion batteries, with pumped water storage being a close second where it's possible. There's a big literature on this. For 12-hour storage capacity, the projected costs are $4,000 per kilowatt hour projected for a few years from now. But by 2040, we'll need 5 trillion watts capacity globally. And to do that, to build out the necessary storage would cost about $1 trillion a year globally for 20 years. So just keep that number in mind, $1 trillion. That's for the storage. It's not the actual PV and wind turbines. But we also have to take into account the current lifetime of lithium-ion is on the order of 10 years. Maybe some people say 15 years. So every once in a while, you're going to have to replace that. And if you take that into account, you're up to $2 trillion in maintenance costs per year. Right? That buys you 12 hours of storage. People don't realize how staggeringly large the storage problem is if you're insisting on going to a high fraction of your grid, your macro grid with renewables. Obviously, you could do things locally because you've got the rest of the grid to back you up. I'm talking about large-scale things. There's gas with carbon sequestration. You know, if you burn natural gas, there's not that much downside if you can take the carbon away. Currently, you can do it, about $200 a ton. There's some prospects for $100 a ton. And the projected emissions in 2040 are 40 billion tons per year if you have a lot of gas. That's going to cost you $4 trillion if you're using the $100 a ton number. Okay, so that's also a big number. And that you have to add that to the raw costs of natural gas. So you're talking about another $2 trillion a year. 6 trillion. So that's just for electricity. That's just for electricity. So now we come to nuclear. I think you know where I'm headed with this. Projected electricity demands equivalent of the output of 2,500 2-gigawatt nuclear reactors. So you'd have to build 125 per year to get up to this number by mid-century or so. If we use the admittedly relatively low cost of South Korean reactors, the current cost to build one is $4 billion. And you need to spend $500 billion, or $500 billion a year to build this out at this rate. It's about 0.6% of current world domestic product to do that. And again, this is just for, this is electricity plus transportation, I should say. Service life of current nuclear reactors is on the order of 80 years, and that's a lot better than 10 years for solar, for example. Now we have an empirical example, just several actually. I'm using Sweden in the 70s and 80s in response to the first oil shock. Sweden built one 4-gigawatt reactor per 10 million residents per year. If you were just to take that number and scale it up to the world population, you could be building 750. But we don't need to build 750. We need more like 125. So yeah, it has been done, and I would argue because it has been done, it's hard to argue that it can't be done. Oh, this is just a graph showing various countries build out over an 11-year period of nuclear power in the past. Sweden, France, Belgium, Switzerland should be on here, but it isn't. Comparing to the build-out rate of, this is energy per person, by the way, of Germany. And so, of course, people talk about nuclear safety, and I think the most important issue there is in proliferation. The other things people talk about I don't think really matter, to be frank. So we have 13,000 premature deaths annually in the United States from coal production and combustion. That's the current number. The current number globally is $8.7 million. This is one of the bad side effects of burning particularly coal, but also other kinds of fossil fuels. And what that means, if you take a very liberal estimate of the deaths of Chernobyl, 60,000 people, that's the Greenpeace estimate, the World Health Organization says 4,000. Fine, let's use 60,000. More people die every 3 days currently from fossil fuel particulates than have died in the whole history of nuclear power. So try to absorb that for a minute. We lose more people in 3 days from fossil fuels than we have had lost in the whole history of nuclear power. This is what people say is dangerous. And by replacing nuclear power plants, as they effectively did in Germany with coal, as it makes absolutely no sense from a safety standpoint. Now, I have this little cartoon that shows the situation. Global warming is the big monster. Nuclear power is the mouse, and these are the environmentalists reacting to the mouse and not being aware of, not taking seriously, I should say, the global warming problem. But of course, one of the tragedies of the cessation of the production of nuclear power in the United States and other Western countries is that we also stopped innovating, largely stopped, not entirely stopped innovating, and yet we have known for 50 years or more that we can do better than the current light water reactors. There are all kinds of ideas, and, molten salt reactors. They're passively safe. I'm not really worried about safe. I actually argue, and I have an essay coming out in the Bulletin of the Atomic Scientists, that the problem with nuclear power in the United States is it's too safe. And I know that sounds facetious. It isn't. If we could double or halve the accident rate of commercial airliners, but at the expense of doubling the airplane ticket costs. If we double the airplane ticket costs, it would drive a lot of people to taking cars. And the mortality would go up from what was supposed to have been a safety thing. This is what we have done in spades around the world, especially in the US, is by not building reactors, we have had to build fossil fuel plants. A lot more people died as a result. I just think it's kind of crazy. I'm much more worried about the proliferation problem than that. But anyway, the molten salt reactors are passively safe. They can help, some of them can help process waste, existing waste from the light water reactors. They operate in pressure. They can run on thorium, which makes them somewhat unsuitable for weapons, and they have long plant lifetimes. There's also small modular. There's all kinds of things we could talk about. One last point is that, there are very large economic, non-climate savings from eliminating fossil fuels. The World Health Organization says 4.2 million premature. That's actually been upped to 8.7. But this is an old slide. Global economic value of life, if you believe the economists, is about 100,000. So by 2040, we could be saving 400 billion per year in the economic value of lives. That would bring the net cost of nuclear to 100 billion a year, or 0.1% of world domestic product. And if you had cheap green energy, whatever its source, would permit large increases in per capita wealth in the developing world. So the energy conversion would likely yield net benefits even before climate change is considered. Climate costs of continued dependence on fossil fuels could be very, very large compared to these numbers, like 3 trillion per year. So just to end up, how do we do this? This is a problem for economists, not for me. But what they all say, almost without exception, is price the negative externalities of carbon emissions. Bedrock free market principle right out of Milton Friedman. 95% of US economists support this. Coal would vanish overnight because of health externalities alone. Markets rather than ideologies would determine the best mix of solutions. But almost everyone says this isn't enough. The government should stimulate innovation more than it's doing now. So that's basically, let me just summarize here. We're altering the composition of the atmosphere at considerable risk to future generations. The tail risks are pretty scary. Where there is risk, there's also opportunity. Cheap, clean power offers pathways to increase the quality of life globally. We need to adopt a combination of different energy sources. By the way, I am not in favor of 100% nuclear. I should have probably put in a slide that said that. I think everything I've seen, it varies a lot from place to place, but in the global average, 60% nuclear, 40% renewables is kind of where you want to be. And that's how Sweden, France, Switzerland, and Belgium did it in the 70s. Current storage limits limit intermittent renewables to less than 40% of market penetration at grid scale. Fission can be ramped up rapidly and economically, but not in the US, I would say, because we've made the regulatory environment too uncompetitive. It's too safe. For God's sakes, the Nuclear Regulatory Commission, I know because I work with them, requires nuclear power plants to be built to withstand a 1 in 10 million year event. That's ridiculous. We have no way of calculating such a thing. All right. This is reflecting the culture, but we should try to change the culture, I would argue. And this is very important. China and Russia are rapidly developing all kinds of green energy, but including nuclear, and for the export market. Last year or 2 years ago, China signed a big contract with Argentina. You're not going to stop that from happening with a Western environmental movement. So your real world choice is you're going to have Russian nuclear power or French or American nuclear power. At present, I would argue some combination of renewable and nuclear energy appears to be optimal. And I would argue that it's feasible to at least decarbonize electricity at about 0.5% of WDP and all energy at 2% of world domestic product. And I would argue that we should spend at least as much as the central cost, and more than that if you have if you're risk averse and want to pay a risk premium. U.S. should participate in the green transformation of the $7 trillion energy market. I'll leave you with that. Sorry to go over time a little.
Oh, that's perfect. Kerry, thank you very much for the really comprehensive review and assessment of where we are in terms of climate change and solutions. I just, maybe, I know there are going to be a lot of questions, but I'd like to just start with one. One of the characteristics of nuclear power. And I think climate change and correction that has always struck and caught my attention is the absence of both political and public will. For example, in the case of nuclear power, we know that wastes are generated. Some of them are toxic for thousands of years and more.
Yep.
And yet there seems to be no public will or political will to deal with nuclear waste. I think in some respects the same is true of climate issues. When you talk to people in the street and you say, look, we're concerned about a 2 or maybe 3 or 4 degree global change in temperature, they just roll their eyes. Kerry, how do you make that understandable to the public so that the will to respond can be activated?
Well, my experience, that's a very good point, Ron. My experience talking to audiences about this is, I would say, make 2 points. First of all, nobody cares if the world's going to warm up 4 degrees. I don't care. The number means nothing to me because I don't care about the mean temperature. The mean temperature isn't the issue. It's a little bit of an issue. It's all about extremes and their frequency. And when you shift a distribution, you have large percentage increases in the tails. It's just simple geometry, even. So I try to do what I've done here is to phrase the problems of risk. The other thing the audiences respond to is trying to look at this as a question of relative risks. What are the risks of nuclear waste? Which I don't, I think it's the issue of nuclear waste is more involved in the proliferation problem than the how you dispose of it problem, but they're of course related, is to say, okay, let's, we deal with risks all the time. What's the relative risk of nuclear waste and fossil fuel waste, where carbon dioxide has to be considered now part of that waste? Which should you be more afraid of? And to tell them that innovation can in fact make some of the certain designs of nuclear fission plants produce waste doesn't last nearly as dangers don't last nearly as long. But the thing that really captivates them, oddly enough, is the market opportunities. They never think about the opportunity. They never think, oh, gee, we could make money by doing this. And in my experience, and it's an empirical statement, is people really respond to that much more than I would have expected.
Yes, may I make a couple of comments?
Yes, go ahead.
One of the greatest things that drive, shall I say, transition in industry is the development of infrastructure. Infrastructures not only provide jobs, but they actually create an internal economic system themselves. I think one of the big problems with nuclear right now is that the infrastructure is hugely lacking, particularly in the sense of removing spent fuels or reusing them, or enabling those spent fuels to be used in other ways that we don't have right now. Just to throw something stupid out there, perhaps, if you could take all your spent fuel, put them into reactors that you could use to drive spaceships, you could basically colonize the solar systems of the stuff. But the thing is that I think that's where the government really needs to come in, is to be able to structure an infrastructure that actually enables you to build these nuclear plants. It will do, I think, 3 things. One is on the economic scale, it will encourage industries and innovation. 2, it will provide new jobs and, it will also provide a great many encouragement, shall I say, to continue that industry to expand. And my third point is that I think it will change the attitude of people towards nuclear energy if they know there's an infrastructure to deal with the risk that it poses.
Yeah, I think those are all excellent points. It's interesting that China's contract with Argentina, I mentioned, stipulates that China will supply the fuel and take away the waste. So from the narrow point of view of the Argentinians, it's an example of what you're talking about. They like it because they don't have to deal with the waste. But it's not obviously a global solution to the problem, but I think it's a good illustration of what you're talking about. Psychologically, in terms of how people react.
I have a question.
Go ahead, John.
And I have no idea the answer to this. But that's why I'm asking the question. Maybe you have the answer. Well, okay, clearly one of the messages today is that the public has a great fear of nuclear. One of the fears of nuclear is, you can't put it anywhere. You can't put it in Nevada, 100 miles from Phoenix, or Arizona, I'm sorry, whatever it is. You can't, and one of them is you can't leak it into the ocean. After Fukushima, Japan wants to slowly put this waste out at sea, and the fishermen and so forth are hysterical about this. The sea is very large. It's most of the surface of the Earth. What if you took the nuclear waste and put it at some deep ocean trench? What would happen?
The only real risk of that is the reason you have deep ocean trenches is they're subduction zones in plate tectonics. So they tend to be geologically active. But it may be that that's only a problem on long timescales. Eventually, and I don't know exactly the timescale, these will get sucked down into the earth by plate subduction and crushed. But then who cares? If they wind up in the mantle, we're talking about timescales of many, many tens of millions of years. So yeah, I just don't know I've heard that suggested before. I don't know what the feasibility or the economics of it is, but it sounds like an interesting idea.
So and my other question on the same thing is, what if it was just evenly dispersed throughout all of the oceans? You've got some high-level nuclear waste. If you dilute it 100 trillion-fold, how dangerous is that?
Well, this is also an area which I know from studying the reaction to Chernobyl is kind of it's emotional, it's psychological, and rationality seldom enters at any significant level. So, for example, this 60,000 deaths that Greenpeace estimates from Chernobyl is using the so-called linear no threshold epidemiological model of mortality and radiation. If taken literally, it would mean that you'd have a spectacular number of deaths of people moving from New York to Denver. In other words, they don't even account for the fact that you disappear down to the noise of natural variations in radiation, and you still make the calculation. I think you should at least stop that calculation when you're down to the level of the background variability, and that's where I think what the World Health Organization did to come up with 4,000. So, yeah, I think the same issues would come up. The environmentalists would say it's dangerous. It's like unsafe at any speed, dangerous at any concentration. And it wouldn't be rational, John, but it would be effective, perhaps. That's the thing I'm worried
I think, if I can make a comment, I think this the conversation now raises the issue that has been of concern, for example, with nuclear waste management for a long time, and that is that the social science aspects of trying to find a site for nuclear waste storage, whether it's deep ocean or Yucca Mountain, has been traumatized by the fact that technologists don't speak very well to the public. And, you have a public that's absolutely frightened. They hear nuclear, it's like the old story about nuclear magnetic resonance imaging for medical practice. You take the word nuclear out and everybody's happy with it. But just think of how badly we have handled that issue. And I think in some respects, Kerry, I think the same may be true in terms of atmospheric and climate issues. You know, the technologists may understand and have reasonable assessments of what's going on, but we're not talking to the public in words that they understand. And I think that's because some technologists in general don't engage social scientists. I think we must. That's my soapbox for today.
I agree with you. I mean, we've done a terrible, terrible job with the marketing of nuclear energy. If we hadn't, we wouldn't be calling it nuclear energy for exactly the reason you said. It's just it's just been terribly marketed to people, and it's too bad. It was we know how effective marketing is. It's a science.
Yeah.
And we've just completely dropped the ball on that. It's too bad.
John, I interrupted you, so go ahead. Sorry.
So one of the interesting things that I sort of took away from something you said was that, maybe our problem is that we live in a democracy. We got to convince everyone in the country, or 60%. I mean, with the situation in the Senate, you got at least 60% of the people in the country agree for any change. Whereas in those places like Russia and China, they see, just a few people at the top need to get the big picture, see the whether either it's the environmental aspect or the financial opportunity aspect, and they're our best hope in this. They're gonna supply the world with nuclear plants. We're financially going to go down the hole. They're going to do great, and the world will be better off for it.
Yeah. And we'll be buying nuclear reactors from China, and they'll be supplying the fuel and taking away the waste. End of our problem.
Right, it's kind of like chips. Think about chips.
Well, there you are. You've got an infrastructure.
I have a question, Ron.
We're not getting the job.
Bob Hughes, go ahead.
Doesn't that mean we have to sell to Congress, not to the public?
Yeah, a good point. I think both, isn't it? It's both public will and I think political will to make these kinds of things happen.
It is, but you have to persuade the public as a means of persuading Congress to some extent. It's interesting that the problems we've been talking about marketing energy aren't by any means limited to nuclear. I spend a lot of time on the coast of Maine, and the fishermen there are dead set against offshore wind turbines, and they actually have fairly good arguments for that. It's because of the cabling actually takes away a lot of potential fishing grounds for them. And the people of Maine are against every kind of energy. So when they tried to build a set of high voltage transmission lines to tap into Quebec hydropower, it's not much cleaner than that. There's huge objections to that. So there's an even larger scale problem as you now have not in my backyard for everything. So we may eventually run out of electricity altogether if that keeps up.
I think Indiana is the word.
I was going to say we had an interesting case here where we wanted to bury the cables under the ground, and suddenly there was this anti-burying of the electric cables under the ground because it's going to create a greater health risk. I have no idea where they got that idea. The problem is really that we seem incapable of getting people to look at things reasonably rationally. That the emotional part of it always seems to win out. And those who oppose anything essentially play on the emotions.
So, Kerry, you have a question?
Yeah, I worked for Stone & Webster for 25 years. And during that course, I built and engineered 5 nuclear power plants. So I had to bear of that. And one thing about the safety is 3 Mile Island was the best thing that ever happened to nuclear power because they had something that wasn't, it was actually physical or evident to prove what happened. And we spent, Stone & Webster made a lot of money for about 2 or 3 years doing baskets for Three Mile Island. So when you say people that nuclear power is overly safe, I can figure that theory. My question though is nuclear waste was always thought that spent chlorides, they had no place to put them. You mentioned China takes the waste from Argentina. What does China do with the waste?
That's a really good question. I don't know. I know what Europe is doing with its waste. They're building a huge repository in very stable bedrock in Finland, but I don't know what China's doing. That's a very good question. I have no idea. Maybe no one knows. No one in the West knows. I don't know.
We have a question from Vince. Vincent?
Yes. Plasma power is another form that has been experimented with, and I believe Japan and Russia have plants utilizing that. To what extent is plasma power perhaps useful in the diversity of energy sources?
I'm not sure I'm familiar with that term, plasma.
I think he's referring to nuclear fusion.
Fusion. Yeah.
No, actually not. It's if you want to look up some background material, Ben Bova, who is a science writer, has written about it, and it is something that at least supposedly claims a lot more energy from fuels that it utilizes with a magnetic field. I don't fully understand it, but plasma is a fourth state of matter, and some of the initial research was done in the United States. And it's at least something that ought to be known about either way, whether it's good or useful or not. It doesn't seem to have quite the same waste disposal issues, but I'm not sure. That's why at least it ought to be looked at. Maybe I'll have to dig into some.
Yeah, I'm sorry, Vincent, but the only thing I know about using plasma is was actually waste disposal.
Yeah.
And then what you do is then you burn other materials, essentially, to get any energy out of it. It was the idea of getting energy out of waste. That's what I recall from it.
Kerry, just to return to a point you made earlier about, whether it's 2-degree change in global temperature or 5, that doesn't worry you as much as the extremes. I think that's what I heard. Is that correct?
Well, I have to be a little careful about that. So I'm not worried about, it's not the wings of the global temperature probability distribution, although that is a concern. It's even if you knew exactly that it would be 3 degrees with no uncertainty, you would still have enormous uncertainty in the hazards that go along with that. The storms,
no, by hazards, do you mean the fact that we're seeing so much of, the rivers are drying up, that more desert expansion?
Yeah. It's the
Are those the extreme weather incidents?
Yeah. It's the extreme weather. It's the heat waves. It's the wildfires, the droughts, the floods. How to relate those to a given amount of global temperature change?
Yeah,
still problematic, even if you knew what the temperature change is going to be.
Right. Okay, we're approaching the end of our session. Let's see anyone else. Bob, I still see your hand. Bob Deering, I still see your hand.
I don't know how to get rid of it.
Oh, okay. Technical glitch.
I did quit getting it up there. Now I don't know how to get it down.
There you go. Okay. Anyone else? Any other questions for Kerry before we come to the end of our hour?
I was just going to, this is not a question, it's just an acronym that goes beyond NIMBY. I put it in the chat, banana. And I heard head of National Grid giving a talk, and one thing they mentioned was, the problem with doing anything in the gas grid is banana. The public's reaction. Somebody in the public has built absolutely nothing anywhere near anything, which is what we were talking about in Maine.
Yeah.
That's a good term. I'll remember it. We're headed to being a banana republic.
Well, Kerry, I want to thank you on behalf of all of the folks who are on the line and the town of Winchester. This forum is named after David Wilson. Dave Wilson, of course, he was a mechanical engineer, one of our colleagues at MIT, And he founded this forum several years before he died. And after his death, we assigned his name to it. So, I want to thank you for joining us. This fall, we have focused most of our attention on energy and issues related to energy. And just to give you a little bit of context, Dan Nocera spoke about his work on solar energy earlier in the fall, and he brought up the same issue you did about the economic development of those poorer nations and the increased demand that's going to manifest as they grow. And he put it in a context that I thought was interesting. He described them as legacy nations and non-legacy nations. And I think that's an interesting way of addressing it. But it makes the point that there are, we're talking about today's demand, and yet there are so many poorer nations that have got to expand their economies. And as they do, the demand's going to grow. And so the concern we have and the concern you've identified becomes even more critical. And again, I'm grateful for you to take time to join us today. And on behalf of everybody, many thanks.
Thank you. It's been very nice chatting with you all.
Right. Yeah, this is a virtual applause, Kerry. Thanks very much.
I'll take it. Thank you.
All right. Take care,
Kerry.
folks.
Bye-bye now. Bye.
Bye.